Hello and welcome to the talk on domain compression. So I'm going to talk about domain compression, and this is joint work with Clement Cannon, Yanjun Han, Zitang San, and Himanshu Tyagi, appeared in Colt last year. And special thanks to Marco Gutesser, Peter Kairuz, Adria Gaskan, and Chen Chu. So what's the framework that we are studying? So we want to consider the following problem where there are a bunch of users or devices. Each of them has their own data, and they transmit this data to a server, which is denoted by this tower, that wants to solve some kind of inference task. Okay. So now the question is, how do we do this? How to enable this under information constraints? So what do we mean by that? Now, each of the users may not have the ability to send the entire data that they have due to various reasons. Maybe there are bandwidth limitations. Maybe the channel itself is very noisy. Maybe they want to preserve privacy of their data samples. Okay, so only constrained observations are available at the server. And the question will be how to enable distributed inference under this setting. So if you want to describe a little more mathematical, it's actually very simple to describe. So you have an underlying domain X, so each of the data lies in X. And we assume that there is an unknown distribution over X that generates these data. So you have n users or n players, so those are devices, and each of them gets one sample. So you have x1 through xn, player I has sample xi, and now each of them is allowed to choose a channel W. So we'll have this script W or calligraphic W, which denotes a set of allowed channels whose input set is X and the output is some Y. Okay. So why do we consider this framework? Is because it can capture many kind of constraints. The easiest, for example, is if we look at all channels whose output set is L bit strings, 0, 1 to the L, then it captures communication constraints. The WL is communication limited channels. If you want to consider private channels, then you can just consider W of rho. I apologize for using rho instead of epsilon, or epsilon was already taken. To be the set of channels for which the following constraint is obeyed. So for any output Y, you are unable to know whether it was X1 that produced it or X2. Okay? And that's the LDP constraint that we have. You can model many more channels by this abstract notion. So what is the setting that we have? So the framework we consider is that at each step, player I will choose. Player I is going to choose a channel WI, which belongs to script W, which belongs to the family of channels, and then passes its own sample through this channel to observe some YI, and this YI is sent to the server. And the server now collects all of these messages and wants to perform some whatever task it had to. Okay. So now all the fun happens in what is allowed for the players to use in order to choose the Ws, because it seems like once they choose Ws, they have nothing to do. They just pass their channel, their sample through W and get the message out. How do they choose Ws is the question. Now that's where all the fun happens. So let's spend a little bit of time on that. So how are we going to choose the Ws? So the easiest is to consider what are called as private coin protocols, where each of the user is going to choose their own W independent of what others do. Now, one way to think of it is you have a hardware that already has the exact channel that's being used by the players. Or you can think of each of the players as using the basic rapport scheme. So all of them use the exact same channel W. You can also have a little more complicated schemes, which we call as public coin protocols, where At the first stage, the referee is going to send a bunch of randomness to all the players. So now it's like the server first sends public coins or shared randomness to all the users. Now all the users are synchronized at the value of the instantiation of U, and that is what they can use to determine their channels. So now there is some kind of dependence that's introduced across the players. Now these are two simultaneous message protocols that are called simultaneous message passing protocols, because all the channels are chosen at the same time. Okay? And one of the questions could be, do public coins help? And we are going to discuss the entire talk on that, and even a nuanced problem at that. And now, of course, you can ask, what about interactive protocols? What are interactive protocols? Basically, the users transmit one at a time, and their channels can be a function of what was done before. So let's just look at this picture. Here, if I want to do this, I can say that, okay, so player 1 sends their message, and now player 2 is able to observe what the first message was and uses it to figure out its channel. Similarly, player 3 is going to use Y1 and Y2, and so on. So now what this obviously gives the scheme more power, because the previous messages can be used to determine the next scheme. However, it can introduce a lot of latency. So we may not want to prefer interactive protocols, although studying their power is extremely interesting. At least should be interesting to most of us, I guess, at least. So let's look at one very simple question. And what's the question? You have the underlying domain X is a set of size K. So you have a discrete set of size K, and you have a known distribution U, which for now just think of as the uniform distribution. So U is the uniform distribution over K elements. Each of the players gets an independent sample from this unknown P. And your goal is to test, is P equal to U, the uniform distribution, or is it at least at a total variation distance of epsilon from U? Okay, and you can say, okay, what's the error probability? Let's fix the error probability to be some small constant, let's say 0.001. And the question is, how many users do we need to solve this under the information constraints that we looked before? And in particular, do public coins help for this task? And that problem was studied before, at least last year in a paper with Manshu and Clement, and another paper with Cody Freitag. We looked at privacy constraints and communication constraints. So if you have no constraints, if there is absolutely no constraints and the users can send their exact sample over the domain of size K to the server, this requires square root K over epsilon square, which has been established much before. And now imagine we have communication constraints. So if you have L-bit communication constraints, what we show is for private coins, you now have to pay more. How much do you have to pay? You have to pay K over 2 to the L more. And for public coins, you have to pay square root of that quantity, square root of K over 2 to the L. Now you may say, okay, what happens for L equal to log K? L equal to log K, it becomes the same as square root K over epsilon square, both of these, which is exactly the optimal sample complexity without constraints. That's because you can use log K bits to precisely send what your sample is. Okay. And now for L bigger than log K, this quantity goes to 0, which is not correct. So there should be another max over this and on. Now let's see what happens. Let's instantiate this for a very simple scheme where you have 1 bit communication per user. So each user can send only 1 bit. Then the number of users you need for under private coin protocols is K to the 3 over 2 over epsilon square. So there is a blow up of K from the unconstrained case. And if you have access to public coins, a lot of it, then it becomes K over epsilon square. So you don't, you gain an advantage of square root K between the private and public coins. And a similar phenomenon was also observed for local differentially private channels, where your blow up is root K or K between private and public coins. Okay. So the question would be, what if we have only S bits of shared randomness available? Okay. So private coin, no shared randomness. Public coin, a lot of shared randomness. What if we have exactly S bits, very little amount of randomness to play with? How does the sample complexity trade off with S? So now this is the referee R in the picture there, and it sends the shared randomness U. We assume U to be an S bit string. Okay, some distribution over of size to the S. Okay, U is S bit string, and that's shared. Why do we consider it? Okay, let's put. Is it even useful, or is the problem interesting? Let's put all of those thoughts aside and look at. Let's look at why we at least were excited about this work. The first is we are going to give a scheme that we call as domain compression, which is a very general tool of using shared randomness to come up with distributed schemes of embedding statistical problems from a large domain size into a much smaller domain size where you can perform tasks much better. Okay, so it's a flavor like Johnson-Linden straw. So you will use the shared randomness to compress the size of the problem. The next is, this is what I was the most, I like the most about the work is this very nice observation that at least was interesting to us, and hopefully many of you will find it interesting. So I'll leave it as an exercise for all of you. So let A1 through AM be non-negative numbers. Y1 through YM are non-negative random variables, okay, non-negative, but they could depend arbitrarily on each other. Okay, there is no restriction on how they depend on each other. And the probability of yi being at least ai is at least a half. So yi's are at least bigger than ai. Then what we can show is that the sum of the yi's is at least the sum of the ai's over 4 with probability at least 1/3. Okay, this is a good exercise and shows some kind of anti-concentration or some kind of tail property with no assumptions on the yi's. So please try to prove this, otherwise the proof is of course in the paper domain compression cold. And in terms of methods, we are going to use deterministic amplification, which will be one of the big tools that we have to use because we have very limited shared randomness. So remember, we have to solve this problem with 99% accuracy or 99.99% accuracy, but many of the results we have will only succeed with probability 49%. How do we boost it? Then the general scheme is, okay, repeat it many times. Okay, if you repeat it many times, you'll need a lot more shared randomness. How do we use the same amount of shared randomness to boost the error probability? We use deterministic amplification from like 80s. This result, beautiful result from Karp, Kippinger, and Sipser. And as far as we know, this is the first time deterministic amplification has been used in statistical inference tasks to prove sample complexity. And our lower bounds are nice, at least I think they are cool. So let's look at what is the question of domain compression. This is the high level question, okay? This is the only technical part of the talk, I think. So you have to come up with a set F of size 2 to the S. What is each of this, what is the script F? It's a set of mappings. So basically each of the element of F is a deterministic mapping from K, from a domain of size K to L. Okay, so you want to come up with 2 to the S mappings, okay, such that whenever you take two distributions P and Q that are supported over K over the domain size and look at the induced distribution over L. So you take P and Q and then you pick uniformly a function and look at the mapping of induced by that function and look at the induced distribution. Now the distance between P and Q should be preserved or should not contract by too much. This is almost like a flavor of Johnson-Linden straws, except the points are now distributions and we are going to look at the induced distributions. So what we want is, we want this L to be as small as possible. So you can map to a small domain. We want theta to be large, so distributions should be far apart as much as possible. We want this to succeed with high probability, so delta should be small and for a suitable notion of distance. And the idea we will use is we are going to use this S-bit randomness to reduce the domain across the players. And the players will, at the first stage, use the shared randomness to compress their samples. and then use private randomness on the small domain, or use just no more randomness after that. Now, basic results, and this again I would like for you to try as an exercise, because this is a much simpler question. So you have consider distributions over size k, distributions over a domain of size k. Now imagine you pick a subset S of size k over 2 over these k elements. So you pick a random subset of size k over 2. And now consider the induced binary distribution that a distribution P induces. So you have a distribution P over K. Once you select a subset, there is a P of S and P of S complement. That's a binary distribution. If I pick random subsets like this, what is the probability that if I pick two distributions, then they will also be far after the mapping? Now that's what this result says, and this is pretty simple to state, and I would like you guys to think about it, how it will work. It's not an exercise. What's interesting is this is a random mapping of size k over 2, requires a lot of bits, a lot of randomness. Can we do it better? And in fact, we show that you can just come up with a set of order k functions. So you can come up with functions, only order k functions for this particular task of mapping to a binary domain, such that again the same property holds, that the distributions will be far. When you pick one of these uniform subsets, to pick any P and Q, when you pick randomly over this subset, they'll be far apart with a constant probability. Again, there is a small catch. The catch is, how do we make this 0.01 into 0.09? Okay, that part essentially is captured by the deterministic amplification. This is a useless algorithm. How do we make it better? Use deterministic amplification across to do some funny things. Now, I just wanted to say that, okay, the results are all optimal. Our dependence on S is optimal. I guess there is no order S factor or anything. It's in the exponent, but the dependence is optimal. Same with L and rho for basically privacy and communication constraints. Finally, I want to conclude by saying that we looked at the role of randomness in distributed inference and gave sharp trade-offs for distributed goodness of fit. Next year, if the organizers invite me again, then hopefully I'll have something interesting to talk. For now, tentatively, I'll talk about interactivity in distributed inference. But who knows, if we have something even cooler than that next time, I'll talk about that. Thank you very much for your attention.